All right, one other topic that we need to discuss when we're looking at solubility of ionic compounds in water, which we characterize by the KSP, is a concept known as saturation. So let's imagine an experiment where we put some solid magnesium hydroxide in a beaker and we fill the beaker with deionized water, and then we stir it with a stir bar or a stir rod. Over time, so we let some time elapse, maybe 30 minutes, and we come back and we find that some of the magnesium hydroxide has dissolved into the water. All right, and if you were to zoom in at the particle level and look at the ions present, what we would find is that you would have magnesium ions and hydroxide ions, and for every magnesium ion, you'd have 2 hydroxide ions. So we're going to make these closed-in circles Mg2 pluses and make these a big open circle and a little open circle. Those are going to be our hydroxide ions. We'd find that there were some of these ions would have dissolved out into the water, and that explains why the amount of solid magnesium hydroxide is less, because some of it's dissolved out into the water. All right. Now, this is also, we know from our calculations, and if you haven't watched the previous video to this on solubility product, please go back and look at that. But we know at this point that in the solution, we know the concentrations of the magnesium ions, which is 1.1 times 10 to the minus 4 molar, and we know that the hydroxide ions have a concentration of 2.2 times 10 to the minus 4 molar. All right. And we know that from doing the KSP calculation. Here's where it gets a little counterintuitive. Let's imagine another experiment where we took this solution. Let's back up. This solution would be in equilibrium, right? We have a situation where we have the amounts of reactants and products are no longer changing. We've waited a long time. We've stirred it. We've tried to get all of it in solution that can, and that's the point we've reached. So we would say this is in equilibrium. We have reactants, we have products, they're both present together in the beaker. Here's where it gets a little counterintuitive. This runs afoul of our understanding from Le Chatelier's principle, but what we're going to do is we're going to add more solid magnesium hydroxide to this. So if we add more magnesium hydroxide in the solid form and then wait for another 30 minutes of stirring, we would come back and we would find that all of that magnesium hydroxide that we just put in is actually still in the beaker. So you add more magnesium hydroxide and it doesn't dissolve. And if you measure the concentrations, the magnesium ions are still at 1.1 times 10 to the minus 4 molar, and the hydroxide ions are still at 2.2 times 10 to the minus 4 molar. And at the particulate level, you would find that you still have, in the same volume we looked at earlier, you still have the same number of magnesiums and hydroxides. And the reason for this, or rather this, we'll deal with the reason in a second, this phenomenon is known as saturation. So when we say that a solution is saturated, we say what we mean by that is that no more of the solid will dissolve. Even if you add more solid, no more of it will dissolve. That is the amount of magnesium and hydroxide ions that this solution will hold. If you think about it, that's what we mean by the word saturation, even in a normal context. Saturation means it can't hold anymore. So the solution up here in the aqueous phase, it can't hold any more magnesium or hydroxides, no matter if you add more solid magnesium hydroxide to it, all right? It's not going to budge. There's no way around it, all right? This seems counterintuitive from Le Chatelier's principle. You would think that if you added a reactant, right, so this is still the same reaction that we've been dealing with, all right? You would think that if you added a reactant, the solution ought to produce more products. But this goes back to the thing we keep saying, that solids have an effective concentration of 1 in solution. In other words, you can't raise their concentration just by adding more of them. They are locked into their lattice as a solid. Their concentration is determined by their density. It doesn't change. We pretend the concentration is 1 out of convenience. What that means is you can add all the solid magnesium hydroxide you want And no, that's not going to change its concentration. It's still an effective concentration of 1. And so adding more doesn't actually result in the reaction proceeding in the forward direction like we would normally expect from Le Chatelier. All right, so when you see these are always like trick questions on exams and quizzes and things, so including mine. And so we're always going to try to get you to think, oh, if we add some more, maybe of the solid, maybe we can get a higher concentration out here. And the fact is that the concentration of the ions remains the same, and the particulate diagram, which is a reflection of the concentration of the ions, also is going to be unchanged.